Hello. 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 Hello, everybody. Welcome back for this afternoon session. So I just had one announcement to make. So we were very sorry to hear that Professor Joseph Polchinski, who is one of the very prominent lights of in our field, passed away recently. And in his memory, we will have some kind of people coming here and talking about him just after the last talk of the session, so around 4:30. So yeah, so that is all the announcement I wanted to make. So before the closing remarks, and if anybody wanted to say anything, please let us know. Okay, I'll hand over to Anindo to chair the session.
Analytic Conformal Bootstrap in 1D.
Okay, thank you. So I would like to begin by thanking the organizers and the staff of ICTS for organizing this wonderful workshop. It's been very enjoyable, my first time in India, and I'm already looking forward to coming back. What I'm going to talk about today is some work which is going to appear quite soon, hopefully, but together with Miguel Paulos about how one can make progress on the conformal bootstrap analytically in one dimension. And if you're interested in learning more about it before our paper comes out, you can also take a look at my paper from the end of 2016. Okay, so my main personal motivation for studying this question is the observation that it's become pretty clear that the conformal bootstrap equations in general dimensions really impose very strong constraints on the CFT data. So this is like a pictorial representation of the bootstrap equation. We expanded the 4-point function in 2 different channels, and as a consequence of it, using some numerical magic, you derive very strong constraints, in this case on the scalar spectrum in Z2 symmetric 3-dimensional CFT. So it turns out that with some extra assumptions, there's this closed region which encircles the 3-dimensional Ising model, or 3-dimensional Ising CFT, and all just a consequence of the underlying principles of the bootstrap. But unfortunately, still to a large extent, these results have been a numerical black box. We're making progress, but we don't really understand completely where all these strong constraints are coming from. So the question which I would like to start addressing is whether we can understand the origin of these constraints analytically, and whether there is some nice underlying analytic structure. So before I'm going to delve into details, let me review where do we stand in terms of the analytic bootstrap up to now. So the field of the bootstrap or conformal bootstrap was born in a seminal paper of Belavin, Polekov, and Zamolodchikov, where they solved using the bootstrap all 2-dimensional CFTs with a center charge between 0 and 1. But that was pretty much the end of the progress for many years, especially thinking about other dimensions. And at the moment, the strongest result, which is true in a number of space-time dimensions, is a result which was published just last year by Simon Caron-Uot in his Lorentzian inversion formula, where the slogan of this formula essentially is that the CFT data of exchanged operators with spin at least 2 is completely fixed by the singularity in the cross channel. So this completely systematized a huge amount of previous results which were obtained about general DCFTs using the so-called large spin expansion. So here is a selection of authors that contributed in an important way to these results. However, an important drawback of this formula or shortcoming is that it doesn't place any obvious constraints on the scalar spectrum. And remember that in the previous slide there was this plot involving just scalar operators in the 3D Ising model. But this formula doesn't really say much about it. Nevertheless, some progress still be made, as done by David Simmons-Duffy in his paper. So the reason why I would like to focus on 1D today, first of all, is that 1D is much simpler than the general D case, but still retains many of its main features. But another important reason for looking at 1D is that in that case, all the operators are scalars. So somehow the one-dimensional bootstrap sees precisely the constraints on the scalar spectrum. Of course, in the general case, there is some communication or some interaction between different spin sectors. But hopefully, if we understand how things work in 1D for the scalars, it will teach us a lot about how scalars behave in general. And I should also mention there's a recent promising approach of a local group using Polyakov's unitary blocks. Okay, so let me start by reviewing conformal symmetry in 1D. Spacetime is a line. It is acted on by the symmetry algebra SO1, which is the same as SO2, R. There are three generators: the translations, dilatations, special conformal transformations. Operators can be classified into primaries and descendants. The primaries are killed by the K when at the origin, and then the eigenvalue under the dilatations is called a scaling dimension. There is no spin, so delta is the only label of a primary operator. Then the theory is completely specified by giving the CFT data, which consists of the scaling dimensions of primaries and their structure constants. An important feature of CFTs in 1D is that they cannot be local. This is because in a CFT, a stress tensor is traceless. So in 1D, a 1x1 matrix, if it's traceless, it's 0. So there is really no stress tensor. And when a theory doesn't have a stress tensor, this really is the same thing as saying it is not a local theory. Nevertheless, there are many examples of such theories. Maybe the most important ones are conformal boundaries, interfaces, or line defects in higher dimensional local CFTs. Recently, there was also a big surge of interest in the SYK model, and Gross and Rosenhaus actually defined a one-dimensional non-local theory, which coincides with the higher limit of the SYK model, and this is actually conformal on the nose, so it satisfies all the axioms which I'm going to use today. And an example which is going to be important at the end of my talk is that you can construct a 1D CFT by taking an arbitrary UV-complete quantum field theory, a two-dimensional UV-complete quantum field theory, and placing it in ADS2. And then the set of boundary correlators satisfies the axioms of a 1D CFT. But then there's a somewhat trivial example of just restricting correlation function of higher D CFTs to a line, but that's not that important. Okay, then let's go into the bootstrap. We will, in the rest of this talk, I'm just going to focus on the 4-point function of a single primary operator, phi. The dimension will be denoted A. This is just a shorthand for the delta phi. I'm going to put those 4 phi's on the line. The 4-point function is in 1D there is only one cross ratio, so the 4-point function is an in principle arbitrary, or by conformal inference leaves it as a in principle arbitrary function of a single conformal cross ratio z, which is defined in terms of position of the 4 operators like this. And I'm going to be staying in the regime where the operators are ordered in this way. So in a physical regime, z is strictly between 0, and 1, and a real number. So then the 4-point function takes this form. There is some conformal covariant prefactor and a function of the conformal cross ratio, and we can expand it in the OPE. So the S-channel OPE takes this form. I have the squares of OPE coefficients of the operators which appear in the OPE times this function g, which is fixed by conformal invariance, is the conformal block. There is a closed formula in terms of a hypergeometric function. The S-channel expansion becomes more and more precise as I decrease z to 0, but there's also a T-channel expansion, which is becoming more, which arises from fusing the x2 operator with the x3 operator, which takes essentially the same form. There is some transformation in front, and then I need to replace the conformal blocks at z with conformal blocks at 1 minus z. But the important fact is that it can be shown rigorously that both of these expansions are convergent in the region when z is between 0 and 1, and they must agree there. So this is the idea of the bootstrap. S-channel and T-channel expansions must be equal to each other. Very non-trivial equation, which is all that I'm going to be studying in the rest of the talk. And I'm going to rewrite it in this form. So I take everything on the same side and write it as a sum with these positive coefficients times these fixed functions, where this fixed function, capital F, is just the difference between the S-channel block and the T-channel block. And that whole thing is equal to 0 because I just put everything on the same side. Now, I told you that the equation is convergent when z is between 0 and 1, but it's going to be useful to actually complexify z. And in that case, it turns out that this equation can be rigorously shown that this equation actually converges in the whole complex z-plane except for the two branch cuts, which start at 0, go to minus infinity, and start at 1, go to plus infinity. So somehow you should think of the 1D bootstrap equation as living in the vector space of functions. These calligraphic f's is some general holomorphic function which is holomorphic in the blue region away from the branch cut, and which is anti-symmetric because the equation is manifestly anti-symmetric under transformation z goes to 1 minus z. And actually, to specify this vector space properly, you also need to impose the correct behavior as z goes to 0, 1, infinity. But I don't want to go into those details. But there are some important subtleties. Okay, that's well. Okay, here we have this equation. It might be constraining, it might not be constraining at all. But let me first show you some simple solutions of this equation. The simplest one are they just arise by putting free fields in ADS2. So I can take a free massive scalar, put it in ADS2. Then the scaling dimension of this field phi is related to its mass and ADS radius using this formula. And the 4-point function of phi on the boundary is just a sum of the 3 possible different Wick contractions, because it's a free theory, so I just Wick contract. It's a sum of these three factors. It can be decomposed in the OPE as follows, where the spectrum consists of 2a, right, is the external dimension plus even integers, and there's a closed formula for the OP coefficients involving some ratio gamma functions. An analogous solution corresponds to the free massive fermion in the bulk. So let A be the scaling dimension, the boundary scaling dimension of this elementary fermion operator. There, the 4-point function is essentially the same as the 4-point function of the boson, except for this extra minus sign with respect to the plus sign, because of antisymmetry when computing the Wick contractions coming from the ordering. Again, I can decompose it in an OPE. This time, the spectrum is shifted with respect to the boson spectrum. It's 2a plus odd integers. And the OP coefficients take a similar form, but they're not quite the same. And we will see that in these cases, one of the simple, almost trivial consequences of this approach, which I'm going to describe, is that the crossing equation actually completely fixes these OP coefficients after we fix the spectrum to be one of these two options. So, in my opinion, the best way to think of the bootstrap equation is to think in terms of dual space. So recall that V was the space of these antisymmetric functions where the bootstrap equation lives. And now when I take an arbitrary element omega of the duals of the space dual to V, I get a bootstrap. I can act with this omega on the original bootstrap equation and get a simple linear equation for the OP coefficient. So originally I had some huge equation parameterized by z, but in this case, for any omega, I just get a simple equation. So you can think of the specifying z as being a special case of this functional, which is just like the evaluation functional at a fixed point. And for convenience, let me define this real function. By the way, these are real functionals, so they map the vectors in V to real numbers. This is an omega of delta I'm going to define as the real function of delta, which arises by applying omega to the bootstrap vector. By bootstrap vector, I'm going to mean the difference between the directional and cross-channel block. Okay, so you can almost say that the most important goal of the analytic bootstrap is to identify a suitable basis for this dual space, to really find a basis which is somehow most revealing, which tells us what is the physical meaning of the bootstrap equation. But what does this really mean? What does a suitable basis mean? If we just start with the evaluation functionals, evaluate the equation at various values of z, it's not very revealing. Numerical bootstrap typically uses some odd order derivatives evaluated at z. It works extremely well. It gives you these beautiful bounds and kings and islands, but it's not very useful for understanding the analytic origin of these bounds. So what suitable is going to mean for me is that I'm going to construct two different bases for this dual space, which completely manifest the crossing symmetry of those simple solutions which I described. They'll manifest the crossing symmetry of the free boson and the free fermion theories. And this will then allow us to study interacting deformations of these theories, which are consistent with crossing completely analytically. So to make progress, I'm going to define another class of functionals, not evaluating, not taking derivatives, but they will take a form of an integral contour. So the functional is specified by some integral kernel. This is the action of the functional omega on the test function f. It has two pieces. The first piece is integrating the test function against the kernel over this little contour, I can just, the natural thing would be to integrate from 0 to 1 against some kernel, but because of antisymmetry, I can restrict it to be between 1/2 and 1. But actually, it turns out that this is not complete in the dual space, so I need to add an extra piece, which for suitable choices of H is actually going to make my space of functionals complete. So I can't really motivate how I arrived at this, but it took a lot of trial and error. You just have to go with the flow. Hopefully one day there's going to be a better physical picture. But I'm going to add to this part another part, which is now a contour integral starting at 1/2 and going up to 1/2 plus I infinity. And to get the basis for the bosons and for the fermions, I need to choose two different signs. Okay, so now I have functionals parametrized by this kernel H, and it looks like H could be arbitrary, but actually, if I want omega to live in the dual space, there are some important constraints on H. It must decay sufficiently fast near 1, and it satisfies this functional equation. Again, I don't have time to explain exactly why, but you can ask me afterwards. And by the way, the analytic structure of H is the same as the analytic structure of the F vectors. So it's analytic everywhere except for this pair of branch cuts. Now, if in addition to that, H satisfies this funny-looking functional equation, you can start with this formula and deform the contour to arrive at a much more suggestive answer. Okay. If you're not familiar with the bootstrap, it might not look too suggestive to you, but actually it already contains much more structure than before. So this is the formula for the action of omega, not on an arbitrary function, but on the bootstrap vector, the f of delta. So the important thing is really this prefactor, this 2 times 1 plus or minus cos, because this prefactor has double zeros precisely at the locations of the spectrum of the theory that we want to study. When the sign is a minus, the zeros are at 2a as a function of delta. The zeros are at 2a plus even integers, and when the sign is positive, the double zeros are at 2a plus odd integers. And then I have this extra factor, which is not going to modify our story very much. So just to make it more concrete, let's consider the Fermionic functionals. In that case, we have the plus sign, and we can for an arbitrary H, I can simplify the expression to look like this. But remember that to arrive at this formula, H must satisfy some very stringent functional equations. So this is really the crux of the matter, that H is not arbitrary, but satisfies some very restrictive functional equations. And actually, one can solve these functional equations analytically for any A, and find out that the solutions are completely classified by the singlet behavior as z goes to 0. So there are two infinite classes of solutions of the functional equations. So two infinite classes of consistent functionals. One has a power law behavior, like z to the minus even integers, as z goes to 0, and the other one the same thing with a logarithm. And now this singularity is extremely important because, first of all, as you see, the prefactor is completely positive, and it would look like this object might be positive as well, as long as H is positive, because these conformal blocks are positive, but actually the integral does not always converge. If delta is sufficiently large, the integral converges, but when delta hits 2a plus 2m plus 1, the integral stops converging and develops a simple pole as a function of delta. So the simple pole is going to cancel one of the double zero. It's going to make the double zero into a simple zero. So in this case, it's possible. Well, for every H, we get a functional, and it's actually possible to see that we get the following behavior of the functionals on the spectrum of the free fermion. First of all the functionals which correspond to H vanish on the free fermion spectrum, but their derivatives have this Kronecker delta. So we are sort of constructing a basis which is dual to the basis of the V vector space, where the basis consists of the free fermion vectors. And the H hats leads to functionals which this time have like a Kronecker delta behavior on the spectrum, but their derivatives always vanishes. And it's possible to show that these functionals form a complete basis for the dual space. So somehow all these H's, they give us a very nice basis, not an overcomplete, but a complete basis for the dual space. Okay, so this might be a bit abstract. And I should also say that we can immediately recover the OP coefficients of the free fermions simply acting with the omega hats on the identity. So you can just get the ratio of gamma functions simply from this fact. Now a few more, to make it again a bit more concrete, when the external dimension is equal to 1/2, there are very simple closed formulas for the h's. So this hm of z is just some linear combination of Legendre polynomials. You can see that as z goes to 0, the behavior is dominated by this large behavior of this Legendre. So indeed, h goes like 1 over z to the minus 2m, sorry, 1 over z to the 2m plus 2. And we can also find, in some cases, the action of this functional. For the omega 0 functional at a equal to 1/2, this is the formula. It looks pretty complicated, but it is the unique functional with the correct structure of zeros. So you find these double zeros at even integers, but actually the double zero at delta equal to 2 is made into a simple zero by this pole, exactly as I was anticipating before. And by the way, this function omega 0 for any a shows that the free fermion maximizes the gap above identity among all unitary 1D solutions to crossing. So for any 1D solution to crossing, the first primary operator must have dimension less than or equal to 2a plus 1. This is simply because for crossing there must be at least one operator in this red region, which is always, well, this point is in general 2a plus 1. So this functional is sort of the reason why we have this upper bound on the gap. In the same way that in the 3D CFTs we can show that there is an upper bound on the gap by finding some functional. So somehow the dream is that maybe one day we are going to be able to find analogous analytic formulas for the functionals of more interesting interacting CFTs, such as the 3D Ising model. It might be a dream. It might be quite realistic. We don't really know yet. Now, when we have these functionals, we can use it to study deformations of a theory. So let's assume that we start with a free fermion solution, which with 2a plus odd integer spectrum, and we deform it a little bit without introducing any new operators in the OPE. So all that we are allowed to do is to modify the scaling dimensions and OPE coefficients of the operators which are already there. So here I wrote down expansion up to the first order in some coupling. For the coupling being equal to 0, we just get a free fermion. And as we move away, we are just introducing some anomalous dimensions and anomalous OP coefficients. Now we impose crossing symmetry on such a deformation, and now we can apply the complete basis of functionals. So let's apply this omega m and expand to the first order in G. And because of the structure of simple and double zeros of the functionals which I described previously, you actually find that all the anomalous dimensions must vanish. And if we apply the omega hats, you find that all the corrections to OP coefficients must vanish. In other words, the free fermion doesn't admit any deformations which are consistent with crossing unless we introduce new states in the OPE. So this is a simple immediate consequence of the bootstrap equations. Now let's move on to the bosonic functionals, where the story is more interesting. There actually is a deformation. So in this case, the formula for the action simplifies to this form. The structure is very similar, except now one functional is sort of missing. The omega 0, which we had for the fermion, doesn't really exist for the bosons. And maybe a more canonical way to say it is that whenever we any consistent bosonic functional which vanishes on the whole spectrum must have at least two simple zeros. So we cannot find a functional which would have double zeros everywhere except for one operator in the spectrum. This is what allowed us to rule out any deformations before. But there is just no such a functional for the bosons. And the complete basis is now quite similar. We still have the omegas and omega hats, but the omegas we only have starting with the index 1, not starting with the index 0. There are still some orthogonality or duality properties of this, which you probably don't have real time to read. But importantly, the first derivative of these functionals at the first operator is never 0. Unlike in the case of the fermion. And as an example, for external a being equal to 1, there's a nice closed formula for the kernels in terms of Legendre polynomials again. But notice that when we set m equal to 0, these Legendres actually cancel against the inhomogeneous piece. So for m equal to 0, we do not have any functional. This is sort of a missing functional that we don't have. Now we can use these functionals to study the deformations of the free boson solution. So let's do the same thing. Let's assume there are no new operators in the OP. At the first order, it's just the free boson, so 2a plus 2n, and the disconnected OP coefficient. Let's expand it to the second order. And as I was anticipating, one functional is missing, so there is a one-parameter family of deformations allowed. But by the way, in this whole thing, we are keeping the external dimension fixed. The only thing that we are deforming is the CFT data while keeping the external a constant. And let me define now the coupling as the anomalous dimension of the first of the phi. This is the phi squared operator. The delta 0 is the dimension of the phi squared operator. So you can think of tuning this deformation parameter by tuning the anomalous dimension of the phi squared. So in that case, you can use the functions which I showed you before to develop a perturbative expansion for the CFT data. So this is the case for when a is equal to 1, which is the boson field in the bulk is massless. So at the leading order, we get just 2, 4, 6, which is the 2a plus even integers. At the next order, there are some rational numbers, and at the next order, we're increasing with transcendentality. In general, the procedure is that having fixed the data up to the jth order, I can use the functional for an operator to determine the CFT data of that operator at the next order. So you can continue this procedure to arbitrarily high orders, and you're going to keep finding higher and higher transcendentality. So you can sort of think that the reason why in Feynman diagrams we find zeta 3s and pi to the 4th is because of functionals which contain some gamma function and polygamma functions, like I showed you before. And this solution actually has a physical interpretation which corresponds to the bosonic field in ADS2. So at a leading order, I just get disconnected pieces. The only deformation consistent with field theory in ADS2 is the contact diagram with no derivatives. So this contact diagram precisely reproduces all these numbers at order g to the 1, and then at the second order in G, I'm computing one loop corrections in the ADS field theory, etc., etc., etc. And the reason why the couplings are fixed is because I made this important assumption that no new operators appear in the OP. In general, when the couplings of the field theory are arbitrary, I'm going to produce new operators in the OP, but not in this case. So this is sort of a 1D version of what was already discovered in higher D in these two papers. This first paper was at 3 level, and the second paper was at 1 loop. This is the loops in ADS paper. But the techniques of these two papers are not available in 1 dimension. So all these results are new to my knowledge. So let me just end with some outlook. It's a very interesting question to actually ask whether this solution to crossing, this deformation which I discussed on a previous slide, exists at a finite coupling. It's not really obvious. And if it exists, there should be some relationship to it to the Sine-Gordon theory in ADS2, because somehow this absence of other states is the same thing as having integrability. Like if you in integrable theory, you don't produce particles. If you scatter 2 particles, you just get 2 particles out. So this condition of not introducing new states is very analogous to integrability, which is why, and there's a unique integrable theory with a single scalar field, which is the Sine-Gordon, so there should be a relationship. One can ask, what is the physical origin of all these kernels, H, which I was describing? I just solved it as a mathematical problem without much physical background. We already kind of understand the relationship of this to the Carnot formula and to the Polyakov bootstrap. And of course, the whole point of it is to go to higher D. So, thank you.
Questions?
The harmonic oscillator also has an SL2 algebra. So have you looked at how that looks from the point of view of the bootstrap?
Is the vacuum invariant under all 3 generators?
No.
Okay.
Just following up on that, the 1 over...
Where are you?
Sorry.
Okay.
The 1 over x squared potential is conformal invariant, but in
the same problem. No, the vacuum. There is no state invariant under all 3 generators, unlike here.
You had the crossing symmetry, taking z to 1 minus z.
Yes.
Another permutation. Is that one automatic?
In 1D it's a bit subtle because this other permutation can only be reached by crossing two operators with each other.
Yes.
So, well, in higher D, the other one is automatic. At least when all the operators are the same, when all the external operators are the same, then the other equation is automatic just by it's true order. It's true block by block. In 1D you would it's not automatic, but I didn't need it.
Since the system is small dimensional, there's more than just bosons and fermions. So have you thought of non-trivial braid statistics?
Actually, I thought about them a little bit. It would be maybe interesting if by doing this deformation you could change the statistics as well. That was one idea, because it looks like sometimes you can flow from the boson to the fermion. I mean, of course, in one spatial dimension, it's not really. There is not much distinction between bosonic and fermionic field theories because there is bosonization, fermionization. Perhaps you're talking about two spatial dimensions where there is braiding. Well, I guess in 1D you can also have braiding. Yeah, right. I think that's just the only thing is a sign. You can maybe absorb the phases. I haven't thought about it properly.
So I can ask something. You were getting these irrational zeta functions by expanding gamma functions. Is that?
Yeah.
So you wouldn't get things like the double zeta function if you expand it.
No, actually, that's not quite true. I was getting it for a combination of expanding this gamma function and doing an infinite sum.
I see.
Maybe the infinite sum could produce also
the double zeta functions. Okay, very interesting. If there are no further questions, let's thank Dalimil.